So now we're going to talk about extreme values of functions on closed intervals. So extreme values are max and min values. And we start this section off with a definition. It says if we have a function and a given domain on that function, function f, domain D, then the function has an absolute maximum value somewhere in that domain at a critical point C if there is a output, a y value that's bigger, greater than or equal to all the other y values. And then a function also has an absolute minimum on that same domain if there's another critical point, C, for which the y value is smaller, less than or equal to all of the other y values. Okay? So we'll have one y value that's bigger than everything else. That would represent the maximum, and one y value that is smaller than everything else. And so looking at this example, we have sine and cosine. Cosine being that pink curve. Cosine has one absolute max at x equals 0 and two absolute min values, one at negative pi over 2 and one at positive pi over 2. But our sine graph on that same interval has a max at x equals pi over 2 and a min at x equals negative pi over 2. So previously we haven't talked about absolute max and min. We've talked about relative or local maximum and minimum values. Okay, so basically what we're going to learn in this chapter is that if there's any function on a closed interval that's continuous, you can find one point that's higher than the rest and one point that's lower than the rest, which would represent the max and the min. So I've pulled a picture in here, and considering the domain restriction, the same function can have different absolute extreme values when the domains vary. So here you'll see we have the same function 4 times, but all with a different domain. So we're dealing with the function y equals x squared. It's shaped like a parabola. We have its natural domain, and then we have 3 other domains. So when we look at that graph and we look at what the domain restriction creates in each of these situations, we can see some different situations of what a max and a min might have. So if we look at example A has no maximum value because that graph goes up to the left and up to the right forever on the domain of all real numbers. It does have an absolute minimum at x equals 0. So considering the closed interval, for example B, from 0 to 2, we are looking at just this part of the curve. And this curve has an absolute min as well as an absolute max. Example C, our third picture here, you'll notice we have an open circle at x equals 0. And the graph goes up forever. So this isn't a closed interval. And when it's not a closed interval, you'll notice that there's no min value because we'll never touch x equals 0. But there is an absolute max. And then on our last example, looking from 0 to 2 as an open interval, because we'll never be able to reach the value at x equals 0 or the value at x equals 2, there is no absolute max or min. So we could still have a relative max or min on that interval. So I'm going to encourage you right now to pause the video, make sure you understand the difference between these 4 pictures if we create different domains. So moving along, we have our first theorem in this section, and it is the extreme value theorem. And what that says is as long as the function is continuous and on a closed interval from A to B, then as long as that interval is closed, and think about the examples we just looked at, then there will be both an absolute max and an absolute minimum somewhere in that closed interval. Okay, so basically as long as it's continuous and it's on a closed interval, there will be a max and a min value. So, thinking about this picture, and so what we will see is there is on each of these closed intervals, meaning we have a finite endpoint on either side, A and B, right? So we're looking at a closed interval, A and B. There are no open values, and it must be continuous. You'll notice that each one of these has a max, capital M, and an absolute min, little m. Whether or not in this first picture they're both at interior points, or in my second picture they're both at an end point. Okay, so we have a maximum and minimum occurring either at an end point or at an interior point, as long as the function is continuous on a closed interval. So just to recap, an absolute maximum or minimum, an absolute extreme value, is different than a local max or minimum, a relative or local extreme value. So if you look at this picture, you'll notice there is only one absolute minimum over here at my end point, A, and then an interior absolute maximum at D. So there's only one absolute max and min. However, we can have multiple max and min values when we start talking about extrema in a relative sense. So there are 2 local maximums. Okay, and a local maximum just says, hey, over here in this vicinity, there's no other y value that is higher than me or greater than me. So we've got 2 local maximums, one of which is an absolute maximum. And then we have 3 low points. We have 3 local minimums. Only one is my absolute minimum. Okay, so that's the difference between an absolute max versus a local max, and then similarly for minimum values. All right, and we have one more theorem and definition that we're going to talk about before we get into some examples. So one thing that we have been starting to notice through our practice with derivatives is that a max or min occurs where the derivative is equal to 0. So, theorem 2, the first derivative theorem for local extreme values, says that if f has a local maximum or minimum value somewhere at an interior point, call it C, of its domain, as long as the derivative is defined at C, then we know the derivative is equal to 0. So if we can determine that some C value represents a max or a min, then we know that the derivative must be equal to 0 there. And we can use this theorem when we're asked to find max and min values because we set the derivative equal to 0. And solving the derivative equal to 0 lets us know where those critical numbers are, where the max and min values will occur. So, main thing we know is that when we let the derivative equal to 0, we're going to be able to find extreme values. So, and reading what I've pulled in from our text here, Theorem 2 says that a function's first derivative is always 0 at an interior point where the function has a local extreme value, a max or min, as long as the derivative is defined there. If we recall, all the domains we consider are intervals or unions of separate intervals, and the only places where a function f can possibly have an extreme value, local or global, local means relative, global means absolute, are at interior points where the derivative is equal to 0, where the derivative is undefined, or at endpoints of the domain. So this last definition says that an interior point of the domain of a function f, where the derivative f prime is equal to 0, or where the derivative f prime is undefined, we call that a critical point. So you notice we're using the letter C here. I'm going to refer to those points C on my interval from A to B, that point somewhere in the middle, my critical point. Okay, so remember, when we start thinking about finding these extreme values, we're going to be looking at setting the derivative equal to 0, determining the critical numbers where it is equal to 0, where it is undefined, and at any endpoints of the domain. So here we have a function, f of x equals x times 4 minus x quantity cubed. We always want to be thinking about domain. And the first thing we'll think about here is what kind of function are we dealing with? And we'll look at it, we'll notice that it's a quartic polynomial. And polynomials have a domain of all real numbers. So we know there are no undefined values here. Okay, so there are no critical values coming from the endpoints of the domain. So our second piece will be to find the derivative. And if I wanted to, I could FOIL all of this out, but I don't want to. I'm going to use my product rule because I have a product of x times the quantity 4 minus x cubed. So my product rule says first times the derivative of the second plus second times the derivative of the first. So in this case, f prime of x is x. The derivative of my second piece is 3 times 4 minus x squared. And I took the derivative of the outside, but this I'm taking the derivative of a composition, which means I need to use my chain rule. So the derivative of the inside is -1 plus 4 minus x quantity cubed times the derivative of the first, and the derivative of the first, derivative of x, is just 1. So my derivative, f prime of x, equals -3x, 4 minus x quantity squared, plus 4 minus x cubed. Now, we're going to need to solve this equal to 0, and right now it's kind of messy for us to deal with. So we're going to factor it. And this is where factoring those GCFs really comes into play. If I look, I have two terms here. I have a first and a second, and they both have a 4 minus x. The first one has 2 of them, and the second term has 3 of them. So I'm going to factor out the least amount. I'm going to factor out 2 of those, and over here with my 3 take away 2, that's going to leave me with just 1. So factoring that out, I end up with f prime of x equals 4 minus x quantity squared, and I'm left with -3x plus 4 minus x. So that plus 4 minus x, that was what was left, that one of them we had left. And in the front, we factored all of them out, so they went away. All right, so we can clean this up a little bit and then it will be really easy for us to solve equal to 0. We have 4 minus x squared and then negative 4x plus 4. And I can see I could pull a negative 4 out here. F prime of x, I'm going to pull that negative 4 out of that second factor, write it in the front. I've got negative 4 minus x squared, and when I pull out the negative 4, that leaves me with x minus 1. So, way easier, in my opinion, than multiplying everything out up here was factoring the GCF. Did you guys really want to cube 4 minus x? I didn't want to. So, now that we found our derivative, and we have it in factored form, I'm going to set it equal to 0. And setting my derivative equal to 0, it's very easy for me to solve and see what my critical numbers would be. That first factor, negative 4 equals 0, can't happen, so I don't need to set that factor equal to 0. But for the other two, I'll get x equals 4 and x equals 1. And, these are my two critical numbers. So this quartic polynomial had two critical numbers, and those are numbers where max and min values could occur. And you'll want to make sure that we paid attention to the fact that it was a polynomial, so there were no undefined values, and that the domain, being negative infinity to positive infinity, had no endpoints.